In section 3.3, we're going to talk about optimization using linear programming. We're going to determine whether a system has a maximum or a minimum. So there are situations that occur in business in which a company hopes to either maximize their profits or minimize costs, and many constraints need to be considered. These issues can be addressed by the use of systems of inequalities and linear programming. So you can use linear programming on a calculator, and it can work really quickly and very fancy. We're going to look at more basic models where we're going to graph the inequalities ourselves and determine a max or a min. So the way to do that is to graph the system. If the inequalities and equations are given, we'll graph them. Otherwise, we'll have to come up with the inequalities first and then graph. After we graph the inequalities, we're going to find the intersection points, the vertices. Once we have the vertices, we're going to plug those points in to our function and determine the values. The highest value will determine our maximum, and the lowest value will determine our minimum. There are two types of situations that happen with linear programming. We either create a bounded region, as in this first example, and as you can see, all three inequalities create this shaded region that's enclosed. In this scenario, you will have both a maximum and a minimum. In the second example, we call this an unbounded region. In an unbounded region, you either have a max or a min, one or the other. And the way we determine whether it's a max or a min is by plugging in those vertices and testing a test point towards that unbounded region. If the unbounded region is larger, then that means only a minimum exists and we can't determine the maximum. If the point near the unbounded region is lower, then that means we can't determine the minimum, so we would have a maximum, which we will look at with more examples during class time. So let's get started with exactly how to do this. In our first example, we just have inequalities that are given to us. It's not a real life situation yet. So what we're going to do is we're going to graph all three inequalities. Let's start with the first one. The first one is saying that y has to be greater than or equal to 3 and less than or equal to 6. Remember, those will be horizontal lines. So I'm going to graph two horizontal lines. You want to make sure you are using straight edges so that you can clearly see the correct intersection points. And remember, there's shading because there's inequalities. It's saying I need to be greater than and at the same time less than. So I'm just going to do it pretty lightly. Here is my first inequality, greater than 3 but less than 6. My second inequality is already in slope-intercept form. So I'm going to plot up at 12, which just happens to be right off the grid, and the slope is 3. So that is to either go up 3 over 1, or in this case, I'm certainly going to go down 3 over 1. And we keep on going. It's super important, that you're plotting plenty of points because we need to clearly see those exact intersection points. And voila, we just got one. And another one. Okay, that 2 will be a solid line. Use a straight edge. It's very tricky for me to make straight lines on this tablet. And we're saying we're less than. So we can put a test point of 0 in, and this would be saying is 0 less than or equal to 3 times 0 plus 12. Is 0 less than or equal to 12? Yes. So we're going to shade everything to the bottom right. Okay, now let's graph our last inequality. And that has a y-intercept of 6 and a slope of negative 2, down 2 over 1, down 2 over 1, up 2 over 1. And a solid line there. That did not go well. I'll do my best. That's a little better. Okay, and my shading there will be below. So now I want to darken in that overlapped region. So that overlapped region is this trapezoid. And what's really important to determine of that overlapped region now are what the vertices are. So I'm going to darken those in. So we can see one vertice here is at -2, +6. One vertice is at -3, 3. One vertice is at 0, 6. And then our other vertice, we have to be really careful with, but it is right in the middle. It's at 1.5, 3. So I'm going to write those 4 vertices in the first column here. So one of them was at -3, 3. Our next one was at -2, 6, 0, 6, and then 1.5, 3. So after you shade all your inequalities, we're finding that bounded region and determining the vertices of that bounded region. It does not matter the order that you put them in, just all the vertices need to be included. Now what I do is I actually go solve what the value of my function would be with those ordered pairs. So the function they gave us is 4x minus 2y. So I'm going to plug those values in for x and y. And you can do all of your calculations. And for the first one, when I plug that in, we get -12 minus 6, so we get -18. The next one, we get -8 minus 12, which is -20. The third one, 0 minus 12 is -12. And the last one is 6 minus 6, which is 0. So now what we want to do is we want to determine what is the maximum and what is the minimum. So we look at these values here. And for the maximum, what's the largest value? Our largest value is 0. And our smallest value is -20. Therefore, the max is 0 at the ordered pair 1.53. And the min is my smallest value, which is -20, and that's at the ordered pair -2, 6. Okay, so with linear optimization, what we're trying to figure out are our maximum and our minimums. Once again, we graph all of the inequalities, we determine the shaded region, what are the vertices of that region, and we take those vertices and plug it into our function that they give us. From there, we determine the highest and lowest value. What I'd like you to try now is number 20. Determine the graph, find the vertices, plug them into my function, and determine what will be the maximum and minimum. Go for it. Now let's look at a real life situation. Okay, so with our real life situation here, it says that optimization is that we need to seek the best price of amount to minimize costs and maximize profit. So our whole goal as a business is to maximize our profits. This is often obtained using linear programming. So there's a little more we need to do this time around because the inequalities will not be given to us. So we need to define our variables. What will our x and our y stand for? We need to write as many inequalities as possible given the constraints. We need to then graph those inequalities and find the vertices. We need to determine what we're trying to maximize and minimize. Are we trying to maximize costs, minimize costs, maximize profit, etc.? Then we need to substitute our vertices into that function and determine what the maximum minimum is. So let's look at this application. Each week, Mackenzie can make 10 to 25 necklaces and 15 to 40 pairs of earrings. If she earns a profit of $3 on each pair of earrings and $5 on each necklace, and she plans to sell at least 30 pieces of jewelry, how can she maximize profit? So, what are the two variables in this situation? What are the two things that we're working with? We're working with necklaces and earrings. So I'm going to define those first. X is going to be the number of necklaces. If you choose X to be your number of earrings, that's fine. Just the inequalities will look a little different. Y will then be the number of earrings. Okay, so I've defined my variables. Now we need to determine what the inequalities and constraints are. So it says Mackenzie can make 10 to 25 necklaces. So she's not going to make less than 10 and she's not going to make more than 25. If necklaces are X, that means one inequality will be that the amount of necklaces has to be greater than or equal to 10, but less than or equal to 25. Then it says 15 to 40 pairs of earrings. So same deal. I'm not going to make less than 15 pairs of earrings, but I can't make more than. So Y will be greater than or equal to 15 and less than or equal to 40. If she profits $3 on each pair of earrings and $5 on each necklace and plans to sell at least 30 pieces of jewelry, how can she maximize profit? Well, that 3 and the 5 are talking about profit. That's going to go towards my function. So in terms of the constraints, I'm going to skip that and continue with the amounts, right? We're talking about numbers of products we're making. So our last inequality here is going to be that she plans to sell at least 30 pieces of jewelry. So the amount of necklaces plus the amount of earrings has to be greater than or equal to 30. So here is my system of inequalities that I'm going to graph. So let's start with that. Let's do the first one. I'll do the first one in teal here. So to do that though, notice it's up to 40s. I'm going to make a note that each one of my intervals here, I'm going to count by 5s. Okay, I'm not going to label all of them, but each one of these is going to be by 5s. Okay, so now I'll continue on. And we want to do X is 10. So X is 10 is a vertical line through 10 and to 25. So 5, 10, 15, 20, 25. And again, please use a straight edge. It'll make it a lot easier and a lot prettier. All right, that shading is that we're going to be between those. All right, my next one I'm going to plot, I'll use orange, and that is my Y has to be between 15. So 15 is the third line up. 15, 20, 25, 30, 35, 40. And I have to be between that. So we can start to see I've formed this rectangular region so far. And lastly, we need to graph our last one, which I'll use green. And I need to put that into slope-intercept form first. So subtract the x, and that gives me negative x plus 30. So 10, 15, 20, 25, 30. And the slope is 1, but since each block is 5 units, I can just go down 1 block over 1 block. And that will work. Okay. And we'll connect that. And now we need to shade. I'm greater than, so that's going to be in this region. And so now I'm going to bold my vertices. So my vertices are where orange, blue, and teal all match. So orange, blue, and green all match. So here's our first, our second, our third, and then we have a grand total of 5. My shaded region is all in here. Okay, so came up with my variables. I determined my constraints, my inequalities. I graphed those, and now I determine my vertices. So I'm going to put those vertices right on in here. Okay, let's see. My first vertice that I see here is 10, 20. Then I have 15, 15. Just going over towards the right now. There's 25, 15. Above that is 25, 40. And then the top left one will be 10, 40. And remember, the charts I'm giving you here, it's just so that you have enough room, but you may not have as many vertices as boxes I give you. Okay, now how do I fill in the rest of the chart? Well, now this is what we're trying to determine is the maximization or minimization. So I need to create a function. So I'll grab purple. The function is all about maximizing profit. So how do I determine profit of these products? Well, I'm making $3 on earrings and 5 on necklaces. So my function, which we call function X and Y here, right? We're looking for both what's the maximization using my X and my Y, is going to be that I get $3 for earrings and $5 for necklaces. Well, X is my necklace, so I'll have 5X and 3Y. So my function I'll use is 5X plus 3Y. So I'll write that into my chart. And now we plug all of our points in and simplify. So 5 times 10 plus 3 times 20, and so forth. We'll keep on going. Last but not least, 5 times 10 plus 3 times 40. Once I plug all those in, I'll calculate. So the first one, we get 50 plus 60 is 110. The second one will give us 120. The third one will give us 170. The fourth one will give us 245. And the third one will give us 170. So when I look at all of those, I'm now trying to determine, remember the question says, what will maximize profit? So which one is the largest? 245. So the question again says, how can she maximize profit? So how can she do that? By what she's selling. So what are we trying to sell? I'm going to circle all of this. And we're trying to sell earrings and necklaces. So we want to look at that ordered pair. So to maximize profit, she will need to sell 25 is my X, so 25 necklaces, and 40 is my Y, 40 earrings. This max profit is $245. I hope that makes sense. Don't forget to go back and finish the other problem.